Effect of medium on electric force. Physics for everyone welcomes you. My name is Kanagaraj Natarajan. So today let us learn about definition of Coulomb force, effect of medium on electric force, expression for electric force in vacuum, expression for electric force in medium, expression for electric force in different medium. Let us learn Coulomb's law. The force of interaction between two stationary point charges in vacuum is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Let two point charges Q1 Q2 be placed in vacuum or free space with permittivity epsilon naught at a distance of r. So F proportional to Q1 Q2, F inversely proportional to r square, so F proportional to 1 by r square. So F depends on medium. So F equals K times Q1 Q2 by R square, where this K depends upon the medium. So let us now write the Coulomb's law in vacuum. F equals 1 by 4 pi epsilon naught Q1 Q2 by R square. Here the K is replaced by 1 by 4 pi epsilon naught. So K equals 1 by 4 pi epsilon naught. The value of this K is 9 into 10 power 9 Newton meter square Coulomb power minus 2. So epsilon naught is the permittivity of free space. Its value is 8.85 into 10 power minus 12 Coulomb square Newton power minus 1 and meter power minus 2 minus 1. So epsilon naught is called the permittivity of free space. So now I am placing the same system in a medium of permittivity epsilon. Now the force decreases to Fm, right? Let us see why it decreases. In a medium of permittivity epsilon, the force between the two point charges is given by Fm equals 1 by 4 pi epsilon Q1 Q2 by R square. Since this epsilon is always greater than epsilon naught, what you understand from here, the Fm is always less than F. So we define the relative permittivity epsilon r equals epsilon by epsilon naught. Relative permittivity is the ratio of permittivity of the medium to the permittivity of the free space. So for vacuum or air, epsilon r equals 1, and for all other media, epsilon r is greater than 1. So Fm equals 1 by 4 pi epsilon naught epsilon r Q1 Q2 by R square. So we remove the medium. So there is a medium. This medium is being removed. Once it's removed, what happens? The force increases to the value capital F. So it increases to F. To go back to the same old force Fm, I'm increasing the distance. Once I increases a distance to r prime, then what happened? The force decreases back to Fm, which it had it in the medium, but right now it is in the vacuum. If we want the charges should be placed in vacuum to have the same force as in the medium, we have to increase the separation between the charges. So 1 by 4 pi epsilon naught Q1 Q2 by R prime square equals 1 by 4 pi epsilon r Q1 Q2 by R square. So cancelling same term on either side, we get R prime square equal to epsilon r square. Taking square root on both sides, we get R prime equals root of epsilon r. A distance of r in medium is equivalent to a distance of a root of epsilon r in vacuum. So Fm equals 1 by 4 pi epsilon naught Q1 q2 by r prime square. Tips and tricks for shortcuts. When a slab of thickness T is placed between the charges, then T is equivalent to root of epsilon r T. So F equals 1 by 4 pi epsilon naught Q1 Q2 by R minus T plus root of epsilon R T the whole square. R minus T is the thickness of air medium, right? The root of epsilon R T is the dielectric equivalent distance in vacuum. So when a slab of thickness T1, T2 with relative permittivity epsilon R1, epsilon R2 are placed in between the charges, then F equals 1 by 4 pi epsilon naught q1 q2 by r minus t1 minus t2 plus root of epsilon r1 t1 plus root of epsilon r2 t2 dot the whole square. Here I have mistakenly done these three dots. Thank you, children.